So any sample of matter will have a certain quantity of energy associated with it. So we're going to define some terms related to the concept of energy and see how that relates to matter. So it's important to recognize that any physical or chemical change is always accompanied by a transfer of energy. So if I'm going to melt an ice cube, I'm going to have to put some heat into my ice cube. When I burn a fuel, some heat, some energy will be released. That's why I'm burning the fuel, to gather that energy that's released. And if an explosion occurs, like a firework being detonated, well, then there's going to be a massive release of energy. So both physical and chemical processes are accompanied by changes in energy. So what do we mean by energy? Well, formally, energy can be defined as the capacity to do work. And by work, we don't mean like, going out and getting a job and, being useful in the world. Work in chemistry and physics is defined as the ability to move an object against a force. Doing work means moving an object against a force. So a good example of what we mean by energy would be lifting an object up higher against the force of gravity. Or we could take two magnets, each of which has a north and south pole, and those magnets, perhaps they're stuck together, and we move them apart from one another against the magnetic force. So whenever we are moving an object against a force, then we are doing work. Whenever an object is moving as the result of a force, then work is being done by that object. So it's kind of this interesting idea. There are a couple of very important forms of energy, and one of those is kinetic energy. And kinetic energy is the type of energy that's associated with movement or motion. And kinetic energy depends upon two things. It depends upon the mass of your object and how fast it is moving. And in particular, what is important to recognize is that if everything else is constant, then as the velocity of your object increases, its kinetic energy increases. And similarly, if everything else is kept constant, as the mass of your object increases, the kinetic energy of your object increases. We say that these two things are directly related to the kinetic energy. So as one of them increases, the other increases. So if I have two objects that are moving at the same velocity, but they have different masses, right? So that's this scenario here where everything else is being kept constant, where the velocity is being kept constant, but the mass is changing. What's going to have the greatest kinetic energy? Well, in this example, it turns out that M1 is bigger than M2. So object 1 will have more kinetic energy than object 2. So this kind of makes sense, right? If I throw, like a little tiny ball bearing at you at, 10 miles per hour, it's going to hit you and you go, ow, not much. But like if, a truck hits you at 10 miles per hour, it's going to hurt a lot, right? So that kind of gives you an idea of that concept. Similarly, if I have two objects that have the same mass, that they're moving at different velocities, then how is that going to affect their kinetic energy? Well, hopefully what you can see is that the object that is moving faster will have more kinetic energy than the object that is moving more slowly. So, if I drive a truck, really bad picture of a truck, into your house at 2 miles per hour, it's not going to do a lot of damage. If I drive a truck into your house, the same truck at 60 miles per hour, it's going to do a lot of damage, right? It has more kinetic energy. So, you can think about these things. So here's a little thought experiment here. It says, which will do more damage, a bus or a compact car hitting your house at 5 miles per hour? Well, the bus has they're both moving at the same velocity, so the velocity is unimportant in here, but the bus is a lot heavier than your compact car, so it's going to do a lot more damage to your house. There's a special kind of kinetic energy that's of interest to chemists, and this is called thermal energy or heat. And what thermal energy or heat is the kinetic energy associated with the random movement of particles. So by particles, we mean molecules or atoms that make up a sample of matter. Some important qualities of thermal energy or heat are that as the temperature of your object increases, the thermal energy of your sample increases. That is, as the temperature of something goes up, its particles start moving around more. So what we know is that the average velocity of the particles that make up a sample of matter will increase with temperature of our sample. Another kind of energy that's really important to chemists is potential energy. And potential energy is the energy associated with position. So this is energy that depends upon where an object is. So if you have a ball that's sitting on the ground, it doesn't have a lot of potential energy. But if you change its position, so it's sitting on a cliff, and then it now suddenly has a lot more potential energy because we've changed its position so that it has greater, what we call gravitational potential energy. So that's a kind of really familiar example. We understand that when an object is raised up, and then it's going to gain a gravitational potential. And if I drop the object, that gravitational potential energy will be converted into kinetic energy. So it'll fall downwards, right? So an object that is raised, when it's released, it will fall downwards, and its gravitational potential energy will be converted into energy of movement. So that's an interesting concept. What we're really learning here is that energy can be converted from one form to another. Interesting, right? There you go. And this makes sense. When you drive your car up a hill, you're turning your kinetic energy into gravitational potential energy. Now, there's a particular form of potential energy that's of interest, especially to chemists, and this is called electrostatic potential energy. And this is a form of energy that depends upon the position of particles that have a property called electrical charge. So electrical charge can be of two types. It can be either positive or it can be negative. If an object doesn't have electrical charge, it's described as being electrically neutral. It has neither positive nor negative charge. And it turns out that the forces between particles that have this property of electrical charge depend upon the position of the particles relative to one another. And in particular, what we know, as described by this thing called Coulomb's law, is that the closer particles are to one another, the stronger this interaction, right? So electrostatic potential energy increases as the particles get closer to one another and decreases as they get further away. Another important property of particles that have this property of electrical charge is that particles that have the same electrical charge will repel one another. They experience a repulsive force between each other, and again, that decreases with the distance between the particles. So when these guys are really close to one another, they interact a lot. When they're further away, they don't interact as much. And that kind of makes logical sense. For particles which have opposite electrical charges, they will attract one another. Okay, they will be drawn towards one another. And again, this force gets stronger the closer the particles are to one another. So, an important quality of, or an important observation about energy is the law of conservation of energy. And the law of conservation of energy states this, something we've already observed, that energy can be converted from one form to another. So kinetic energy can be turned into potential energy, and potential energy can be turned into kinetic energy, for example. It can be transferred between different objects. If I give you a push, then my movement, my energy of movement is transferred to you, right? So you can transfer it between two objects, like when two objects collide. But energy cannot be created or destroyed. There's a fixed amount of energy in the universe, and it just moves from one object to another, and it gets transferred from one form to another but the total amount of energy in the universe is unchanging. It's neither increasing nor decreasing because energy cannot be created or destroyed. It just moves from one place to another and changes from one form to another. So energy flows or energy moves from one place or from one object to other objects. Now, it does this according to certain patterns. For example, energy will spontaneously move via heat transfer from a hotter object to a cooler object and never the other way around. So heat always moves from a hot object into a colder object. Now, you can try this out at home if you want. If you turn the stovetop on and get it nice and hot, you can put your hand on it and I guarantee your cold hand will get hot. It will never be the other way around, that heat flows from your cold hand into the stove, making it hotter. That just never, ever, ever occurs. Now, that's kind of a dumb experiment, but you could try it the other way and maybe put your hot hand into the fridge, and you will find that heat will flow from your hot hand into the cold fridge and your hand will get cold, right? So it always goes from the hotter object to the colder object. So this is interesting to think about. If you put ice cubes into water, what is happening? Well, conventional wisdom will tell you that the ice cubes make the water cold. Well, it's really probably more correct to say that the water is making the ice hot, because what's actually happening is heat is moving from the water into the cold ice cube. And what you recognize is that as we transfer heat into an object, is if you transfer enough heat into an object, you can actually get it to change its state. And so if you put, ice cubes in your drink, eventually those ice cubes will absorb so much heat that they will melt and become liquid. So for how long does heat flow? When does this heat stop flowing? Well, heat will flow from a hotter object to a colder object until the objects have reached the same temperature. That's why when you pour a cold glass of water, heat will flow from the room into your cold glass of water until your water is at the same temperature as the room. So when objects come to the same temperature, we say that they have come to what's called thermal equilibrium. Okay, so they reach the same temperature, and we're going to use that observation later on when we start doing some calculations. So here's an interesting problem concerning the conservation of energy, and we're looking at the exchange between kinetic energy and potential energy. So you're asked to consider a cyclist who is not moving. So what we really mean is that their kinetic energy equals 0. They're not moving, they are stopped. But you can see that they have some potential energy, right? So as we raise this cyclist above the lowest point there, potential energy increases, right? So here they have some potential energy, 1, 2, 3, 4, 5, 6 lines above the lowest point, but they have no kinetic energy. And then as they kind of go over this slope, what's going to happen? They're going to start rolling. The potential energy will decrease, but the kinetic energy will increase. And then as they hit this bottom here, they're going to start rising again. So what's going to happen? They're going to slow down. They're going to gain some potential energy, but lose some kinetic energy. And then they're going to roll down this slope here, losing a whole bunch of potential energy, but getting faster and faster and faster and gaining kinetic energy. And then they're going to reach this bottom here where they have the minimum amount of potential energy, but the maximum amount of kinetic energy. And then they're going to start rolling up the other side. Now, they can never end up with more energy than what they started with, which was when we were on this line. So at point E, they're going to grind to a halt, they're going to stop moving, and they're going to roll backwards. Okay? And that's what's going to happen. Now, in this system, we're assuming that there's no friction or any other forms of energy other than kinetic energy and potential energy. So these guys would just kind of, keep rolling backwards and forwards, backwards and forwards, backwards and forwards, right? So the highest point they can get to is where they started. Yeah, you can't get that because they start with no kinetic energy. Now, if they had a little bit of a run-up, they had some kinetic energy and some potential energy, then they could get a little higher. But they can't in this case because they started when they were stopped. So where would the bicyclist have the highest potential energy? And I guess you can, this is a little bit sort of confusing, but you could pick either A or E. They would never get to F though. So let's say A. A is where they're going to have the highest potential energy. And then it says, where would the bicyclist have the lowest potential energy? Remember, potential energy decreases as they fall down. So that's got to be D. And then it says, where would the bicyclist have the highest kinetic energy? Where would they be going the fastest? Well, they're going to be going the fastest right at the bottom of that hill there. So that's going to be D. And that also explains why they have the lowest potential energy at D, right? And then it says, where would the cyclist have the highest speed? So again, that's where they've got the maximum kinetic energy. So that's going to be at D. And then it says, would the cyclist's kinetic energy be higher at D or A? So the kinetic energy at A is 0, right? We pointed that out right at the beginning because they are stopped. And at D, they're going to be going the fastest. So they're going to have the highest kinetic energy at D. And then it says, would the cyclist's potential energy be higher at D or A? Well, they don't have any. That's the lowest point as far above the ground is at D. So that's when they've got the lowest potential energy. And A is where their potential energy is the highest because they are the highest above the ground. So it's got to be A. Just make sure we're not misreading a higher for a lower or anything. And then this next one is interested. Would the cyclist's total energy be higher at D or A? The important thing is that the energy doesn't change, right? It just gets converted from one form to another. So the total energy that we have at the beginning is the same as the total energy at any point along the path. You just got different amounts of potential energy and kinetic energy. So the answer to that one is going to be no. And there we go. And then it says, suppose the cyclist lets off the brakes and coasts down into the valley without pedaling. Even if there is no friction or air resistance to slow him down, what is the furthest point that they can reach? Well, they can't get higher. They can't get more energy than what they started with. So the best they can do, where they're going to roll to is E. Now, if they pedaled a little bit, they could get up to F if they put some extra energy in, but they're not pedaling. And they probably, in reality, wouldn't get quite all the way up to E because they'd be slowed down by air resistance and also by friction in the system, but they told you to ignore that, so we're going to say E. Okay, so that concludes this little short section on some of the fundamentals about energy. And yeah, if you have any trouble with the content, please reach out to me.